Okay, so we are back here for the rest of the chemistry lecture, and I know you're thinking, oh, this is not why I took anatomy, to learn more chemistry. But try to hang in there and keep in mind that this chemistry, this biochemistry, is really important for understanding the physiology of the human body. If you think about it, we're these big bags of chemicals, and there's all kinds of metabolic reactions that have to go on in the body to allow us to function. So to understand those metabolic reactions, you really do need some of this basic biochemistry. So hang in there with me while we get through this last bit of chemistry. Hopefully I can get through most of this in this lecture, but I may have to put a little bit into the next one. Okay, so we left off at polar covalent bonds. Now remember that covalent bonds, let me bring this back up here. Remember that covalent bonds are going to be bonds that are based on sharing of electrons. And we talked about, and just as kind of a quick reminder, when we talked about some of the different bonds, we first talked about ionic bonds. Remember, ionic bonds, just to give you a quick review, ionic bonds are where you're actually transferring an electron and forming ions, right? Because as you give up an electron, you have a positive charge here. As this one takes on an electron, it ends up with a full negative charge. So we make these, remember, cations and anions, right? When we form these ionic bonds. And the ionic bond is based solely on attraction of the positive and the negative charges. So they're just positive and opposites attract, right? The positive and negative charges are attracted to each other, and that's what forms the ionic bond. Now, when we're talking about covalent bonds are formed by the sharing of electrons. And so there's no transferring, they're all sharing the electrons. And so in this case here, when you're making methane, the hydrogens are sharing those electrons with the carbon, and vice versa. Carbon's sharing its electron with the hydrogen. And to fill everyone's outer shell, remember carbon here is going to have a full outer shell with 8 electrons, including, again, it's including those ones that it's the hydrogen sharing with it. And then vice versa, the hydrogens, remember, only want to have an electron shell with 2 electrons in it. So those hydrogens are nice and happy as well. And so again, this covalent bond is based on sharing. Now, non-polar covalent bonds are where the electrons are shared equally. Okay, so again, if you have the hydrogen and hydrogen here bonded together to make a hydrogen molecule, we'll talk about that term in just a minute. Molecule, again, being that they're the 2 of the same atoms here, bonded together. So they're going to form this non-polar covalent bond because the electrons are actually going to be shared equally. There's no electron bully here. Both of the atoms are sharing those electrons equally. So the electrons are spending an equal amount of time around this hydrogen as they are around this hydrogen. Okay, so this results in an electrically balanced, what we call non-polar molecule. And that non-polar molecule, again, is not going to be charged as a molecule. Now, on the other side of things, we have, oh, and then carbon dioxide is a nice example of a non-polar molecule, non-polar covalent with non-polar covalent bonds. Again, making up this non-polar molecule as a whole. And we call them non-polar because there's no charge to the molecule as a whole. Okay, now you'll see this is going to be different than when we form polar covalent bonds. So with polar covalent bonds, you have what's called an electron bully. And what that means is that the electrons are actually not shared equally between the 2 atoms. Usually, one of the atoms is what's called more electronegative, and it really, really wants those electrons. And so it has a stronger attraction for those electrons. And what ends up happening is it pulls those electrons closer to it, and the electrons spend more time with it. So in this case, chlorine, really, it already has a lot of protons in it. It really wants those electrons to fill its outer shell. And so it's going to have a stronger pull on those electrons. And what that means is they're still shared. They're still sharing the electrons, but just not equally. This is kind of like, if you had a big brother and they were supposed to share toys with you, right? And maybe it was your, favorite, was a favorite car, okay? And that favorite car was not equally shared. Maybe your brother kept the car for like, 3/4 of the time, and you got it for just 1/4 of the time. And that's kind of what's happening here in terms of the electrons. The electrons are spending more time closer to the chlorine than they are to the hydrogen. And what happens here is that ends up leaving us with these partial charges. And actually, I'm going to do this. I'm going to talk about this with water in just a minute. But in this case here, because the electrons are spending more time with that chlorine, it leaves it with a kind of partial negative charge. And then that leaves that hydrogen with a partial positive charge. So the reason that this becomes really important is when we talk about water. And again, remember that we are made up, majority of us, when we look at, the molecules inside our body, we're mostly water, right? And so it's really important to understand the properties of water and the fact that water is a polar molecule. And the reason is that these oxygen-hydrogen bonds here are polar covalent bonds. So what ends up happening again is that oxygen is the more electronegative one. So it's going to have a greater pull. It's going to be the bully on those shared electrons. And those shared electrons are going to spend more time with it. So because of that, it's going to give that oxygen a partial negative charge. And we usually draw to show that it's not a full negative charge, right? It's not like the forming the ions. It's not taking that extra electron all to itself. It's still sharing it. It's just that it's spending more time closer to it. Okay. And so when this happens, that leaves this oxygen with a partial negative charge. And then of course, these hydrogens with a partial positive charge, since the electrons again, are spending less time with it. And what ends up happening is this leaves us with a molecule that has two different charges, kind of two different charged ends, really. It has a negatively charged end here and a positively charged end. And we call this, when anytime a molecule, again, has two different charges in it, we call it a dipole. Okay, so it literally has di means two, right? Pole, polar kind of opposite ends. So we have these two poles, a positive pole end and a negative pole end here. Okay, so that becomes really important when we talk about some of these properties of water. So again, this just kind of is showing you here we've got, ions with a complete transfer of electrons here forming our cations and anions. And then we have our polar covalent bonds where we end up with these partial charges, right? So we'll end up with a lot of molecules that end up being dipoles. And then we have our nonpolar covalent bonds, which these guys are perfectly happy. They are content by themselves because there's equal sharing of electrons and there's no charges. So these guys, because they are charged, they'll want to interact with each other. And this is why, right, salt dissolves in water, because water is a polar molecule. And so what will end up happening is if you take sodium chloride, your salt, and you mix it in water, what's going to end up happening is as you mix those ions around, then that sodium can form again a partial, bond here with this the negative charge here. So to form that attraction to that partial negative charge of the oxygen, and the chlorine will form an attraction to that partial positive charge of the hydrogen. So that's why we can mix salt and water, right? Is because of this property that water is polar. And this is really important because we're going to talk about this a lot, and being that water, again, is great for transporting things because it's polar, because it will interact with other charged particles. So, and itself, right? So, I mean, the great part about this is that water molecules like to interact with themselves. And so you guys know this again when we talk about, if you look at your water inside your bottled water, let me get my pen on here, but you know that water molecules like to interact with each other, right? And that's why they like to stick together. Oh, my drawing is, I don't know why I have such a hard time with, I have a bamboo here, but I always seem to have a hard time with this. Okay, so let me see if I can get over here and draw another one here. So you've got the oxygen here that's negatively charged, right? And then here you have now your hydrogens. And they have these, again, partial. I'm drawing a partial positive. I should have drawn up here. This is a partial negative. And another hydrogen here. And that's a partial positive. And so when one water molecule bumps into another water molecule, okay, then they can form what's called a hydrogen bond. And I know I'm probably getting ahead. Oh, no, here, I'm actually on the slide. I didn't even look at what slide I was on. I'm on the slide. Look at me. I'm actually where I need to be. So they form what's called a hydrogen bond. And this hydrogen bond is based on partial attractions here. So we have the partial positive, okay, here of the hydrogen end. And as it bounces into another water molecule, it's going to be attracted to that partial negative of the oxygen. And it's going to form this little temporary bond called a hydrogen bond. So when you look at your water molecules at room temperature, the water molecules are actually constantly bouncing around, right? Because how much our molecules are moving depends on how much heat is added to them, right? And so as they bounce around, they'll actually break these hydrogen bonds here, okay? And then form new ones with the water molecule next to them. So as they're bouncing around, when you look at your water in your glass, it doesn't seem like much is happening, right? But actually the water molecules are constantly bouncing around and they're making new hydrogen bonds and breaking hydrogen bonds. And so, they're not monogamous. Okay, your hydrogen bonding between water molecules, they're not monogamous, and they're constantly bouncing around and then making a bond with a partner next to them. And so again, this is one of the things that gives water this wonderful property as a liquid. So again, hydrogen bonds are this attractive force between the electropositive hydrogen. So again, it's that partial positive hydrogen of one molecule and the electronegative atom of another. And again, in this case, if it's another water molecule, it's that oxygen, right? So it's not a true bond. It's more of this kind of weak magnetic attraction. And so it's this kind of temporary bond, right? And again, this is common between dipoles such as water and water. You have two water molecules, which is what makes water liquid, that it can do this. It can constantly, and that's why, again, it doesn't have to keep that same form. You pour your water out on your desk and it's not going to stay solid there, right? Because it can break bonds and form new bonds with all these other water molecules as you. So that's what gives it the fluidity, right? If it's solid, like if you were to freeze water, right? Then you're taking away the energy that's in those water molecules and they're slowing down as you freeze them. And once you hit that freezing point, those water molecules have slowed down and they've really formed this nice crystalline pattern, right? And so they're stationary. Now, as you heat those water molecules up, then they'll start to move and bounce around. And then again, you go from a solid to a liquid and it becomes more fluid. So again, this property of water and being able to form these hydrogen bonds is also what it's going to give, what is going to give water its ability to exist in all three states naturally. So we'll talk about that. I know I'm getting ahead of myself here, but we'll talk about that as well. Um, so again, this is just showing those hydrogen bonds forming between the electronegative oxygen and the electropositive hydrogen end of these water molecules. And again, it shows these kind of temporary bonds, these temporary attractions that form. Now, this gives water its surface tension because of the hydrogen bonding. It allows something like a water strider, right, to walk on water because of those hydrogen bonds. Now, you might not think that those hydrogen bonds, right, they don't seem like they're all that strong because they can be broken. But, right, when there's lots of them, and I'm talking about millions upon millions of them, like if you're going to do a belly flop in your pool, right, you felt all of those hydrogen bonds, the strength of all those hydrogen bonds as you belly flopped in the water, right? You broke those hydrogen bonds, but still you felt the strength of those hydrogen bonds as you hit the surface, and we call that surface tension of the water. Okay, so that gives us a little bit on the properties of water. We'll talk more about the properties of water kind of coming up and really throughout kind of all 201 and 202. So now we're going to talk a little bit about chemical equations and chemical reactions. And I love my I try to put my cartoons in here to keep this humorous for you guys. I really seriously do. I think you're overreacting. Oh, come on. Chemical reactions. Anyway, so when we talk about these chemical reactions, this is the fact that chemical bonds are, when they're formed, they can be rearranged and they can be broken, okay? And so when we do these chemical reactions, right, it's easy for us to display them as what's called a chemical equation written out in our symbolic form. And that way then we can, demonstrate our reactants, which are the substances that are going into the reaction, right? So what kinds of molecules or compounds do we have going into the reaction? And then our products. What do we have that's coming out of the reaction after things are broken and rearranged, okay? And the amount of the reactants in the products are shown in these nice balanced equations. So when we do these, again, compounds are always going to be represented as these molecular formulas. So when we write the molecular formula, we're just telling you that here this is a molecule or compound, again, because there's two different atoms. So we can say a molecular compound that is covalently bonded and has two hydrogens and one oxygen, okay? We're not showing you how, right? Although we kind of all know how water molecules look, but it just gives you that molecular formula, what's in it. Another example is C6H12O6, which is glucose. I give you a second to kind of think about it. Glucose, right? And so again, it's just telling you that in a glucose molecule, you have 6 carbons, 12 hydrogens, 6 oxygens bonded to each other. So again, the subscripts indicate kind of how many of the atoms are joined by the bonds. And a prefix like this denotes the number of unjoined atoms. So if you say here 2H2O, it means you have 2 water molecules, okay? So they're not covalently bonded, right, to each other. You just have a water molecule here. And, oh, that takes me so long to draw this here. Let me see if I can use my pen here. Water molecule here. And you have a water molecule here. Oops, sorry, guys. And you have a water molecule here. I almost did it again. Water molecule here. Okay, so it just means that you have 2 water molecules. So again, just kind of, this is basic chemistry, kind of hopefully you remember most of this. But when we do these reactions, these chemical equations, and we show them in this molecular formula, we're going to write the reactants, okay, on the left side, and then we'll show an arrow as the chemical reaction occurs, and then the product on the right side. So here you've got a hydrogen plus a hydrogen, and you make, lo and behold, a hydrogen molecule, right? We call that a molecule because they're both, hydrogen atoms bonded together are of the same atoms, or same element, I should say. So then when you have atoms from different elements like this, okay, we form a compound. You can still call it a molecule, but it's also called a compound. And so in this case, for our reactants, we have 4 hydrogen plus 1 carbon gives us methane. And so again, just kind of some really basic terminology on how we, some basic kind of chemistry terminology on how we demonstrate our chemical equations. So when we look at the types of reactions, and this is going to become more important for us, there are three main types of chemical reactions, and we're going to talk a lot about these chemical reactions all throughout the semester for 201 and 202 when we talk about metabolic reactions. So some of the chemical reactions that occur in our body are synthesis reactions, right? And so synthesis is just like it sounds, guys. You're taking your reactants and combining them together to form a larger, more complex molecule, okay? And so we use these synthesis reactions in what we call anabolic processes. This is anabolic. You can think of anabolic steroids, like building, right? We call anabolic steroids anabolic because anabolic means building, right? So when we have an anabolic reaction, it's a building reaction where you're taking these basic building blocks, like in this case, amino acids, and you're putting them together to form a protein molecule, okay? So the opposite, so there's our synthesis reaction, right? The opposite of that is what's called our decomposition reactions. And decomposition reactions are breaking down the larger complex molecules into its constituent atoms, right? So it's basic building blocks. So for example, when you have this big molecule like glycogen, right? So glycogen is a form in which we store our carbohydrates, and we'll talk about this later on in 202. But many of you probably know this if you've ever done like carbohydrate loading. Your goal in terms of like doing your training ahead of time and then, carbohydrate loading the night before is that you're going to help your body to hold on to more glycogen stores. And so those are kind of heavy carbohydrates, but if you're doing, like a really long run or something the next day, then you want to quickly be able to break this down into these glucose molecules so you can use those glucose molecules, those simple sugars, right? So we call this process of decomposition reactions where we break things down catabolic. So catabolic, again, is bond-breaking reactions. So you can think of anabolic processes are synthesis reactions, and catabolic processes where we're breaking bonds are decomposition reactions. So, and then there's these weird reactions that we call exchange reactions. Also sometimes called displacement reactions because you're displacing some of these reactants with each other. But again, exchange reactions. I like exchange reactions, so it's kind of more common one I use. And this involves both synthesis and decomposition because oftentimes you're breaking bonds between one of the reactants and then making a new bond with one of the reactants, okay? So you'll see there's a neat example of this with I'm not going to click on this and show this to you because it's too long, but there's this great little video where they actually use the Flintstones to describe all these reactions. So the last two reactions, again, are going to be exchange reactions in this video, and it's kind of a cute one with the Rubbles and the Flintstones, and they show, they go to a dance and end up crossing over with each other. So it's a really good example of like Barney ends up with Wilma, they're initially or at the end of the reaction. So it's just, if you like that, it might help you to understand these reactions. It's kind of a fun one. But anyway, again, the really basic here is, if you have A bonded to B, covalently bonded to B, and C covalently bonded to D. And then again, you have an enzyme or something that comes along to catalyze this reaction. And then A forms a bond with D and B forms a bond with C. Now, an example of this is ATP transfers sometimes its terminal phosphate group to glucose to form glucose phosphate. And so it does this in these metabolic processes, right? Yeah, that we'll get into kind of more in later on in the semester here. But so here, to form that glucose phosphate, you will break one of these phosphate bonds and then bond that phosphate to a glucose to form glucose phosphate. So again, this is just an exchange reaction. So sorry, I was going to get into explaining glucose phosphate more, but sometimes I get ahead of myself, so I will try to keep it simple. It's hard to not tie everything together right now for you, but okay. So we also have so again, we have synthesis reactions, we have decomposition reactions, and then we have exchange reactions. Now, we also have one other type of reaction that we have to talk about. In living systems, a lot of our exchange reactions that we have, so this is part of the exchange reactions, kind of a subcategory, if you'll say, of exchange reactions, is we do have these reactions called redox reactions. I know you're like, redox. So these are the reduction oxidation, right? That's why we call them redox, reduction and then oxidation. And so what this means is that atoms are reduced. We say that atoms are reduced when they gain electrons. And the reason that they're reduced is because they're like, kind of gaining negative charge, right? Because electrons are negative. So if they're gaining electrons, they're gaining a negative charge. And so that reduces their overall charge, more negative, less positive, if that makes sense. It's really hard to remember this. And then oxidized is when they lose electrons. So I know this is hard to remember. You're like, I sort of remember this from 181, but I tried to tune it out. So the easy way to kind of remember this is oil rig, if you remember. Some of you may have gotten this. Oxidation is loss, which means that you're going to lose an electron. So whichever of these is oxidized is going to lose electrons, and reduction is gain. So in this example, we have glucose plus 6 oxygen results in this exchange reaction, right? Where we're exchanging some of these atoms are going to be bonding now with new atoms from other molecules. And we're going to end up with 6 carbon dioxide, 6 water, and ATP, right? This is that byproduct of cellular respiration, if you remember. So in this example, glucose here is the one that's being oxidized. It's actually going to lose its electrons. And oxygen is the molecule that's going to be reduced. Oxygen is going to actually gain electrons as it forms its bonds here. So that's our redox reactions. Again, just so that you understand the base of redox, I'm not gonna give you a bunch of chemical reactions and ask you to go through all those, but just kind of as a reminder of what that is. So all chemical reactions, when we talk about now the energy flow, so those are the types of chemical reactions. When we actually talk about the energy flow of these reactions, the reactions are either going to be exergonic or endergonic. Exergonic, okay, the exergonic reactions are going to give off energy. They're going to have a release of energy, okay? And so I don't know if you can think of, trying to think of a good way for you to remember exergonic, but I always can say there's kind of 2 ways. You can remember it as exit. So energy is going to exit the reaction, okay? So EX, exergonic, exit, energy is being released. It's exiting the reaction, giving off energy. Or you can think of like the exorcist, right? And so the exorcist is like giving off demons or whatever, So that's another way if that helps you remember it. I know stretching here, but I try to give you guys some things that help you remember this. But with these exergonic reactions, again, the products are going to have less potential energy than the reactants because energy was given off, right? in the process of the reaction. So oftentimes, again, our exergonic reactions are going to be catabolic and oxidative reactions, okay? So these catabolic oxidative reactions are going to be things like what happens, in digestion as we break down these molecules and give off energy that can be used to make things like ATP, right? So for example, like we talked about in cellular respiration, right? That's the whole basis for cellular respiration, is that we're taking this glucose molecule, these high energy bonds in this glucose molecule, breaking those bonds in a series of reactions, okay, that makes up this process of cellular respiration. And each time we do these catabolic reactions, we're going to capture some of that net energy that's released and use it to make ATP, okay? So that whole reaction of cellular respiration is this a bunch of exergonic reactions, right? When we talk about things like the Krebs cycle. Now, endergonic reactions are going to be these reactions that result in a net absorption of energy. So they're going to need energy. They're going to use energy. So the products are actually going to have more potential energy than the reactants, because you're taking in energy and then storing it in some of those new bonds, right, to make the products. These are going to be our anabolic building reactions. So for example, when you take amino acids, right, you're going to have to take in a bunch of energy to put those amino acids together to make a protein, right? Because the energy to make those bonds just doesn't appear from nowhere. So this is an endergonic, if you call these amino acids here. To put these amino acids together and form these peptide bonds, we got to take in some energy, and that's an endergonic reaction. Now, many of our chemical reactions are theoretically reversible. And I say theoretically because oftentimes our reactions will occur, but at a rate that is really slow. And so we need these things called enzymes. So I'm going to talk about them in just a minute. I know I'm getting ahead of myself, but so it's theoretically reversible if we have enzymes to help speed up and make the reactions happen. But, so that's theoretically. So theoretically, the reactions can go both ways. You can, again, in this direction, be a synthesis reaction, right? And then later on, when you want to break this down, then it can be a decomposition reaction, and you can break it back down. So theoretically, again, they can go both directions depending on what enzymes you have available. Now, again, chemical equilibrium, we call that, occurs if neither a forward nor reverse reaction is dominant, okay? So the same number of synthesis reactions as decomposition reactions are happening. And many of our biological reactions aren't always reversible. And that's because to go the opposite direction, and the energy requirement is too high, okay? Or we don't have the products, okay? So if we don't have enough of the products, we're making this, but it's getting used elsewhere, okay? Then there's not enough of the product to, do the opposite reaction. But we're going to talk about this because there are some really important reactions that are reversible like this. And we'll talk about this especially when we get to some of the buffers in our blood and blood chemistry. So it's really important. Rate of chemical reactions. So there are things that can speed up chemical reactions, right? So temperature. We know temperature increases rates of reactions, and it does this by simply just, when you heat things up, right, you're increasing the movements of the molecules and increasing the chances that they're going to bump into each other and react to each other, right? So that's how you increase the rate of reaction with temperature. It's simply by just increasing the movements of the molecules. And as they move around faster and faster, they're more likely to bump into each other and react. Also simply just adding more reactants, right? So if you've got more of the reactants, then they're same thing. They're more likely to bump into each other and interact each other and form bonds or break bonds, okay? So again, that's another way that you can increase concentration, or increase the speed of a chemical reaction, is by increasing the concentration of the reactants. And then the particle size. So smaller particles usually tend to increase the rate, believe it or not. And again, not just because it oftentimes allows for more surface area for interactions, because you got these smaller molecules that can kind of fit in between, smaller particles that can kind of fit in between things. So again, particle size also makes a difference. So those are the three major things that are going to speed up a chemical reaction, other than enzymes. So then our fourth thing that we have, okay, so again, we got temperature, increasing temperature, increasing concentration of reactants, decreasing the particle size, or we can add a catalyst. And a catalyst is simply, as you probably remember, anything that's going to increase the rate of reaction without actually being a part of the chemical reaction. So it's not going to, the catalyst itself is not going to interact with the reactants, like in the terms of it's not going to make a bond with any of the reactants. It's just there to help kind of reduce the energy that's needed for that reaction to happen. So it comes out, the catalyst at the end of this comes out unchanged itself, okay? And so obviously we're going to talk about enzymes because enzymes are the biological catalysts. So catalysts, we can talk about catalysts in terms of chemical reactions, right? There's non-biological chemical catalysts if you're just, wanting to speed up a chemical reaction. But in this case, we're going to obviously focus on the biological catalysts. So you can just think of enzymes, okay? Because enzymes are going to be what's our major catalyst inside the human body. And enzymes are so very important that honestly, none of the metabolic reactions in your body would happen fast enough for you if we didn't have enzymes. So they would happen so slowly that none of the reactions would occur. So what we need is, we need these enzymes to help lower the activation energy. And so I talk about that in the next PowerPoint here. So again, we'll get more into enzymes, but just kind of remember that just as a basis, the fourth thing that can speed up a chemical reaction is your enzymes, your biological catalysts. Oh, and then, sorry, I just totally skipped over my funny cartoon for you here, just to keep you, going through my chemistry lecture here. It says, what happens when chemists hop on social media? And so this was too funny. Oxygen and potassium went for a date, and it's totally okay. Get it? Because the oxygen and potassium symbol is K. And so I know you guys, it's killing you. And then it says, don't tell me yesterday I saw oxygen with magnesium. And I was like, OMG, oxygen, and then MG, magnesium. He is cheating on potassium. So anyway, you can read some of these. They're just funny. The comments are funny. Again, what happens when biologists and chemists post on social media. Sometimes it can be quite dangerous, right? We have our own sense of humor. I know it's always interesting. Okay, so let me go ahead. I want to get right into this part 2 here. So this is the second part of the chemistry lecture, and it's really going to be focused more on the biochemistry, which is nice. So the last part was kind of review of some basic chemistry, and so this will really get into more of the biochemistry. And so that's really, again, the studying the chemical composition and the reactions that are happening in living organisms, right? This is what we're really interested in. When I finally got to biochemistry in college, I was like, oh, finally, right? Finally, the chemistry I'd been waiting for. And so when we talk about biochemical reactions, all these chemical reactions are either going to be organic or inorganic. When we talk about inorganic compounds, these are going to be things like water and salts and a lot of your acids and bases when you talk about the human body that don't actually contain carbon, and more importantly, they don't contain carbon bound to a hydrogen, right? And I say this because you might say, well, what about carbon dioxide? Carbon dioxide, let's write this down here, sorry. Carbon dioxide contains carbon, and it is not an organic compound. So let's put carbon dioxide here to remind you that carbon dioxide, or you can put it over here, carbon dioxide is not a organic compound. So that's why I kind of put this over here. Does not contain carbon or carbon-hydrogen bonds, okay? Because if it doesn't contain these carbon-hydrogen bonds, then it's going to be the inorganic form of carbon, okay? So when we talk about our organic compounds, these are going to be compounds that contain carbon and hydrogen, okay? Carbon and hydrogen bound together. And we're going to see covalent bonds, okay? Now, inorganic compounds, again, can have covalent bonds too, but they also can have ionic bonds. When we talk about organic compounds are not they're not ionically bound together, okay? They're covalent, always covalent bonded together. So anything that has an ionic bond, boom, you can throw it in the inorganic compounds, okay? No carbon and an ionic bond, it's in the inorganic group here. So again, organic compounds are going to be things like carbohydrates, fats, or we call them lipids, proteins, and nucleic acids, which of course we're going to spend a lot of time talking about in just a minute. And so again, they contain carbon, are usually large, and are covalently bonded, again, to hydrogen. I say that they can be covalently bonded to other things, but they have to have some carbon-hydrogen bonds in there somewhere. Both are equally essential for life. So you may say, okay, well, the organic things are the only things that are important, but that's not true because, we're obviously made mostly of water, right? Salts are extremely important for many of the processes that occur, especially, a nerve conduction. So we couldn't do nerve conduction without salts like sodium and potassium, right? Acids and bases are extremely important. We'll talk about that in terms of the buffer system in our blood and things like that. So we couldn't digest food properly in the stomach if we didn't have acids. So, when we say inorganic compounds and organic compounds, both of them are very valuable and essential for life, okay? So when we talk about inorganic compounds, of course, water comes to mind because it's the most abundant inorganic compound. And it's going to account for anywhere from 60 to 80% of the volume of living cells, okay? So the majority of our cells are water. And it's the most important inorganic compound because it has all these really great properties. One, it has a really high heat capacity. And if you remember, what that means is it takes a lot of energy to change the temperature of water, right? It's the reason that your pool, being this large body of water, doesn't change, the temperature doesn't change nearly as drastically as the air temperature does around it. And again, that's because water has this high heat capacity. It has this ability to really kind of store heat, right? And it takes a lot of energy, a lot more energy to change the temperature of water than it does to change the temperature of the surrounding air. Okay, so that's why, of course, his fish here is saying, oh, I love the specific heat capacity of water, because again, it keeps this environment more stable, especially if you're an ectothermic organism. Now, it also has a high heat of vaporization. So again, that just means that it's going to take a lot of energy, right, to cause water to evaporate. It also is polar. So again, it's this molecule that's charged, right? It has partial charges, and that allows it to interact with other water molecules and gives it some of these really great properties. It also allows it to interact with other charged molecules. So again, this becomes really, really important. And as we get into talking about the cell and some of the properties of the cell and the membrane, cell membrane, it's going to be really important to remember that water molecules are polar, okay? They're charged and they like to interact with other charged molecules. And so then because they're charged, they're reactive. They have this reactivity to them. Again, if they were nonpolar, they wouldn't want to react with anything. And then, of course, they end up providing kind of cushion, right? So you guys kind of can feel that, right? You've got water, and that water helps absorb, impacts and things like that. So again, it provides this kind of cushioning property. And that's because, again, of those hydrogen bonds that form between water molecules. Now, salt, being another inorganic compound, again, also very important inside the human body. And these salts are these ionic compounds, again, that are formed based on, again, these bonds of attraction between an anion and a cation. And what happens is they can dissociate and separate in water. So when you mix, something like sodium chloride, you take your salt and you dump it in water and you stir it. You add a little energy, stir it, and really kind of increase the chances that the sodium and the chloride ions are going to come into contact with those partially positive and partially negative charged parts of the water molecules. And so then you can separate these salts into its cations, those positively charged molecules like sodium, and the anions, the negatively charged ones like chlorine. So this includes everything but hydrogen and hydroxide ions. And that's because we're going to put these in their own special category. These ions are given their own special category of acids, as you probably well know, and bases, okay? So we don't put them in the category of salts, acids and bases. So salts are important because all of these ions that are really important, and especially important to us, we call electrolytes, because they can actually conduct electrical currents in a solution. And this is going to become really important to understand when, again, we talk about nerve conduction and the movement of sodium and potassium. So again, really important at the end of the semester. We'll really focus a lot on that. So these ions play these very specialized roles in different body functions, especially sodium and potassium, super important in terms of nerve conduction, calcium, super important in terms of muscle contraction, and then iron we'll talk about again being in the blood and how important it is in terms of, again, carrying oxygen, carbon dioxide, things like that. So ionic balance is really important for homeostasis. And so it's important to kind of keep tabs, right, on some of these electrolytes. You guys have probably all felt when you've kind of been like deprived of electrolytes, maybe you've done some really strenuous energy and you've really been sweating and released some of those electrolytes and you feel like you need to take some in. So again, these electrolytes are very important for functions throughout the body. And these are just a few of the common salts like sodium chloride, calcium carbonate, potassium chloride, calcium phosphates, or just kind of a few of those. You don't have to know them, but we're just going to talk about them throughout 201 and 202. So again, we don't expect that you know them all now. You will by the time you finish 202. Acids and bases. Acids and bases are both electrolytes. They ionize and dissociate in water. And so when we talk about acids, when they dissociate, anytime an acid breaks up or dissociates in water, it's going to release hydrogen ions. Okay, and those hydrogen ions are what make it acidic. Okay, so these bare protons, they have no electrons, are released into solution. So for example, if you have hydrochloric acid, right, we'll talk about this in terms of our stomach acid. If you've got hydrochloric acid, it will dissociate in water into hydrogen ions and chloride ions. And these hydrogen ions, again, are what's going to increase the acidity, right, of that solution. So that's what happens again when we talk about hydrochloric acid being released into the stomach. And so here's my little funny cartoon on that, since lemon juice, as you're going to find out, is quite acidic here. So important acids that we'll talk about: hydrochloric acid, we'll talk about acetic acid, which is kind of your basic vinegar, right? And then carbonic acid, we're going to talk a lot about in 202. You'll spend some quality time talking about carbonic acid at the beginning of 202, because that is going to be a major player in blood pH. Okay, so Bases are going to be just the opposite, right? They're going to be what are called proton acceptors. So they're actually going to take out hydrogen ions from solution. So acids are going to dump hydrogen ions in solution, okay, increasing the hydrogen ions. And bases are going to take out hydrogen ions from the solution. They're going to bind them up. So, for example, if you have something called sodium hydroxide, which is a really strong base, when you put sodium hydroxide in water, it's going to dissociate into sodium, which is just a basic ion, right? But this hydroxide, okay, ion can now go and bind up. It'll bind to, be attracted to hydrogen ions. And lo and behold, what do you think it's going to form? Water, okay? And it can form a nice water molecule. So that hydroxide ion will take out hydrogen ions from solution, okay, and form water. So again, when a base dissolves in solution, it releases hydroxyl ions, and those hydroxyl ions will bind up the hydrogen ions. Now, there are other bases that work in a very similar fashion. So it's not always releasing a hydroxyl ion, but it's releasing an ion that's going to bind to a hydrogen ion, okay? And so in this case, when you talk about the bicarbonate buffer system, this will be important in terms of blood chemistry, and we'll talk about that bicarbonate having the ability to bind to a hydrogen ion, okay, forming carbonic acid. So it also, again, carbonic acid can release a hydrogen ion. So this is going to be a beautiful buffer system, because you have this bicarbonate ion that can, if there's excess hydrogen ions, bind up those excess hydrogen ions. Again, or, then you can also have hydrogen ions. If you've got hydrogen ions in solutions, it's also releasing hydrogen ions. So it's just beautiful little buffer system that helps to control our pH in the blood. Again, way more than you need to know right now, but I just like to introduce the importance of acids and bases. So that bicarbonate ion will kind of come back as an important base, because it can bind to hydrogen ions in the blood. So pH. We have this lovely pH scale to actually be able to measure, right, the concentration of hydrogen ions in a solution. So the more hydrogen ions there are in a solution, the more acidic that solution is. Now, this becomes confusing because we represent pH as this negative logarithmic scale of hydrogen ions. So, for example, if you have something that is pH 7, right? Technically, it has 1 times 10 to the negative 7th, right? Hydrogen ions. Or, that's the same thing as like basically 1 over 10 to the 7th hydrogen ions, okay? So if you have something that has 1 over 10 to the negative 7th ions, and 1 over 10 to the negative 6th ions here, okay? This, if you remember from some of your basic math, right? This has 10 times more, it's 10 times larger, okay, than this. So that's why I know that for some of you this might be too much math, but for some of you that kind of have this kind of basic math, kind of remember it. It's more in the kind of front of your brain here, then this makes sense as to why things that are lower on the acid base pH scale technically have more hydrogen ions. And that's because it's represented as this negative logarithm of the concentration of hydrogen ions in moles per liter. Okay. So if that helps some of you, if it confuses some of you, just go ahead and ignore that. And then you can just remember that as you move lower down on the pH scale, things are going to be more acidic, more hydrogen ions. The other thing that you have to remember again is it is logarithmic. And all that means is that it's a 10-fold difference between each pH unit. Okay. So if there's something that has a pH 5, a solution that has a pH of 5, it's actually 10 times more acidic than a pH 6 solution. Okay. So, and I'll kind of go through some examples of this in just a minute. So again, acidic solutions have higher hydrogen ion concentration, but a lower pH, okay? So high hydrogen ion, low pH. And that ranged from 0 to 6.99. pH 7 is what we consider to be neutral. So there's an equal number of hydrogen ions and hydroxide ions kind of balancing each other out, forming water, right? So pure water is pH neutral because the hydrogen and the hydroxide ions are bound to each other. And so we call that pH 7. And then alkaline solutions have low hydrogen ions, but high pH. So they're represented in the range of 7 to 14, well, 7.01, technically right above, right neutral, to 14. That's your alkaline or basic range. Remember, alkaline and basic just mean the same thing. So here's some examples of that. And so you can see here your blood pH is usually around 7.4, So if for some reason, you're at the hospital and they're doing blood pHs and all of a sudden your blood pH comes out to be 6.4 and you're like, oh, well, no big deal. It's only a change of 1 unit on the pH scale. No big deal. But remember that this is logarithmic. So what this means is that now your blood is 10 times more acidic than it's supposed to be, okay? Because remember, we're going lower on the pH scale. So that means it has 10 times more hydrogen, not 1 time more, 10 times more the hydrogen ions than it's supposed to have. And that's really bad for blood pH, okay? So a change like that on the pH scale is a big deal for the human body, okay? Now again, if for some reason it dropped down to, let's say your blood pH dropped down to 5.4, which is closer to like what, coffee is. Here, now you've increased the acidity another 10 times. So when you talk about that, okay, if you had a blood pH, this would be really bad. Like you're on your way out, dude, 5.4. You've got a blood pH of 5.4. That means that your blood is 100 times more acidic because again, remember this is logarithmic, right? So this is 10 times 10. So your blood is 100 times more acidic than it's supposed to be. Okay. So that's more like if your blood was closer to the pH of black coffee. So as we all know, because we've all had, too much coffee, right? It's a little acidic. And so this just kind of gives you a nice idea of how that logarithmic scale works in terms of pH. You can see it gives you an idea of some things that, are acidic. Wine is pretty acidic at 2.5 to 3.5, depending on the wine. Lemon juice is about the same as gastric juice here, which is around pH 2. And that's because gastric juice, we'll talk about the stomach releases hydrochloric acid into the stomach. So we'll talk about that gastric juice being a pH of about 2. And then here, pure hydrochloric acid down here is pH of 0. So obviously that's your extreme acid end. And then, you can go on the opposite end here and talk about things that are alkaline. So, egg whites are slightly alkaline. You might say, oh, well, things that are alkaline are better, right? But, when you talk about things that are really extremely basic and alkaline, they can do quite a bit of damage as well in terms of our living human body systems, right? Because again, anything that's too far away from our normal pH can cause problems unless it's contained inside, a special organ like the stomach. And so we'll talk all about that when you get into 202 in the digestive system. But things like lye up here at pH 13.5, obviously very harmful. Sodium hydroxide, you can't take in straight sodium hydroxide into your body. Household ammonia, bleach. So again, some of these things that are too basic can also cause problems inside your body as well. Again, everything's kind of this nice balance, and so we'll talk about the importance of different bases and acids inside the human body. Neutralization reactions are when acids and bases are mixed together. And we have this exchange reaction, right? Displacement or exchange reaction occurs. And what results is water and a salt, okay? So in this case, sodium hydroxide and hydrochloric acid will come together in this neutralization reaction. Base here, here's your base, and here's your acid going in as the reactants. And then your product, okay, from this reaction is just a salt and water. So those are some neutralization reactions. Now buffers, again, I really kind of mentioned this in terms of blood. Buffers are where you have something that will bind to hydrogen ions in solution, but again, acidity really involves just your free hydrogen ions in solution. So not hydrogen ions that are bound to any anions. So what buffers are going to do is they're going to resist these big swings in pH, okay? And this is important because, right, in our blood, we need our blood to maintain this normal pH. And we'll talk about this in terms of enzymatic function in just a minute. But enzymes like to function at a certain pH. And so if the pH swings too much, then those enzymes don't function. Our metabolic reactions shut down and death occurs, right? So that's a bad thing. So we need these buffers inside our system to help resist large swings either way, right? So they're going to resist a large swing to the base side of things, and they'll resist a large swing to the acidic side of things. So buffers can actually do both. They can actually release hydrogen ions if the pH rises and becomes too basic or alkaline. And then they can also bind hydrogen ions if the pH falls, okay? So if the pH becomes too acidic. So they can convert strong acids or bases into weaker ones. And what happens is this is what happens in the blood with this carbonic acid bicarbonate system, okay? It's a really important buffer system of the blood. So again, what I want you to really know right now is what buffers do, okay? I'm going to introduce this carbonic acid bicarbonate system, but please, I will not expect you to memorize this yet. You'll get into it when you get into 202, but I like to mention it now because maybe, by the time you get to 202, you'll be like, oh, I heard this before, it's not so new. So again, this carbonic acid bicarbonate system is really important because this carbonic acid is actually a fairly weak acid. And what can happen is, this is our buffer, right? And what can happen is if, pH ends up, if we are responding to a rise in pH, then what we can do is we can, carbonic acid will break down into bicarbonate, which is a weak base, and hydrogen ions, and release a bunch of hydrogen ions into solution. Now, if for some reason there are too many hydrogen ions in the solution, okay, So just too many out there. And so remember, this is a weak base, weak electron acceptor. So but this is strong, these hydrogen ions being released in solution. So again, this helps to counter that rise in pH, or counter that rise in the basic solution of the blood. So that's what happens if we have a rise in pH. Now, for some reason, we have a drop in pH, and all of a sudden there's a lot of hydrogen ions floating around in your blood, and you're like, whoa, things are becoming too acidic in the blood. Then what can happen is that bicarbonate can actually bind to then some of those hydrogen ions. Because it's more likely to bump into them if they're here and here and here and here, versus before, maybe there was just a few here and here. But now they're like, they're all over the place. So if they're all over the place, then that bicarbonate is much more likely to bind up to some of those hydrogen ions and form this weak acid, carbonic acid. Okay, so this is a buffer system. Now, of course, it only works to some extent. If you've got the extreme acid or extreme base on either end, then it can only help so much, right? But it does help to buffer some of these big swings in pH to a point, right? To a point. Okay, so again, I just really want you to know what buffers are, but I wanted to just give you a little introduction to that buffer system, because you are going to get that into it too. Okay, now let's move on to organic compounds here. So when we talk about organic compounds, we talked about that these are going to be containing carbon, and especially carbon-hydrogen bonds. So again, our exceptions are going to be things like carbon dioxide, carbon monoxide, which are inorganic because they don't contain carbon-hydrogen bonds, carbon bonded covalently to hydrogen somewhere in there. Now, carbon is electroneutral, and so it likes to share electrons, right? It doesn't ever gain or lose them. It's not giving up electrons or gaining electrons. It wants to form these covalent bonds, and it wants 4 covalent bonds, because remember that carbon has 4 electrons in its outer shell. Remember, it wants to have 8, so it wants to form 4 more bonds here, okay? So that it can share 4 more electrons and then fill its outer shell. So that's carbon, right? And carbon is unique to these living systems because it likes to form these covalent bonds. And so it likes to form a lot of these compounds that are necessary for life. And so the 4 major compounds that are necessary for life are carbohydrates, lipids, proteins, and nucleic acids. So really quick, when we talk about the synthesis of these organic compounds, most of these organic compounds are going to be polymers. And so they're going to be chains of these similar units that we call monomers, which are the building blocks. So I know you kind of remember our monomers here are the basic building blocks, and when we put them together in a chain, we form these polymers. And to do this, we do this by a very important reaction called dehydration synthesis. And so remember, it's going to be a synthesis reaction, but it's going to require removing a water, okay, from these molecules to form this polymer. And then you'll see we'll do the reverse and break down these polymers into the monomers. We're going to do this by a process called hydrolysis, which is going to require a water. So let me really quickly explain these. So here, this is a dehydration synthesis reaction. We have a monomer, the building block 1 here, put together with another monomer here. And you can see what's going to happen. This is why we call it dehydration synthesis, is we're going to remove a water molecule and form a bond between these 2 monomers. So we're going to take out a hydroxide ion here and a hydrogen ion here. They're going to come together to make H2O, a water molecule. And now we can form a bond between this monomer and the oxygen here with this monomer. So monomers, again, are going to be linked by these covalent bonds. So again, this is going to be a really important reaction because when we talk about making things like carbohydrates and proteins and lipids, to make these carbohydrates and these proteins and these lipids, excuse my phone here, that we need to do this process called dehydration synthesis. Now, the reverse of this is called hydrolysis. So we're going to take these monomers that are going to be linked by this covalent bond here, and we're going to lyse. That's the reason it's called hydrolysis, right? We are going to lyse a water molecule, hydro, water, lysis. Lysis means to break apart, remember? So we're going to break apart this water molecule, and we're going to add on just the reverse now, an OH group, a hydroxyl group onto one monomer, and then a hydrogen onto the other monomer. So again, it's called hydrolysis because it requires the water, and we are lysing that water. So again, this is going to be a decomposition, a very special decomposition reaction again that we're going to see in the human body quite a bit. Oh, sorry. So this is this is our example of our decomposition reaction that's going to occur, right? Because we're breaking apart that monomer. So the nice part is to remember this, dehydration synthesis. This helps you to remember you're removing water, you're dehydrating, you're pulling out of water. And then hydrolysis will help you to remember that you have to lyse the water and put it on the ends of these molecules to lyse the molecule. So you can think of lysis, right? Lysis. And then here, this shows you an actual reaction that occurs using dehydration synthesis, and then the reverse can happen when you're breaking it down via hydrolysis. So if you look here, you've got glucose, which we're all familiar with, and then fructose, again, another sugar that's commonly found in fruit. And if you put glucose and fructose together, right, and you remove water, you dehydrate out the water, then you can form what's called sucrose, which is your table sugar, okay? So we did a beautiful dehydration synthesis, right? We synthesized a sucrose molecule, which is actually called a disaccharide. We'll talk about these are each monosaccharides in just a minute when we talk about carbohydrates. And then we can actually break this bond here, right? By lysing a water, hydrolysis, and then putting the back on that hydrogen, okay, here on that fructose end to make fructose, and the hydroxyl group on here to make glucose. So again, we needed to consume a water to do that. So again, just kind of a good review of dehydration synthesis and hydrolysis, which are reactions that we're going to use to make all these major carbohydrates, lipids, and nucleic acids and proteins. So I am going to go ahead and break this up. I will put the very last bit of this is just a little bit in a short lecture for you, and then that way then it'll break this up just a little bit. Okay, so please, again, let me know if you have any questions or concerns, and we'll finish this last bit of chemistry and then move on to cells.